All right, so in the last chapter, we were talking about being able to eliminate stuff to get alkenes, right? And what can we eliminate to get an alkene? We can eliminate water from alcohols in a dehydration reaction, or we can eliminate what else? Pardon? Halogen, right? But more than just a halogen, what else was in the elimination? And an adjacent hydrogen. So we were eliminating HX or H2O, right, to get alkenes. Well, we can do exactly the reverse of that. We can add things to alkenes to get new molecules. Those are called addition reactions. And that's what we're going to talk about in Chapter 8. Okay? So just like we can remove H2O from an alcohol to get an alkene, what do you think we can add to an alkene to get an alcohol? If I'm eliminating water from an alcohol to get an alkene, what do I have to add to an alkene to get an alcohol? Water. It's just the reverse. So what can I add to an alkene to get an alkyl halide? HX. That's exactly right. This chapter is going to be talking about the reverse reactions of what we talked about in Chapter 7. Okay? And this is the chapter where we really start building your toolbox of tools to allow you to make all kinds of organic molecules. You can add all kinds of things to alkenes, and we will talk about it more than just in this chapter. This chapter is just a start, okay? But we're going to start talking about addition reactions, okay? And like I mentioned, right, we can prepare alkenes by eliminations. What's this? KOC parentheses CH33. What is that? What? It's a salt. What is it? What kind of salt is it? Is it an acid? Is it a base? It's tert-butoxide. Is it? What is it? It's a base, right? So we're using a base to eliminate an acid to get an alkene, right? And we had a major product and a minor product. Can you explain why we get the major product? Zaitsev's rule. That's right, Zaitsev's rule. Are we going through a carbocation here? We could, because it's a tertiary alkyl halide, but what lets me know that this is an E2 elimination and not an E1 elimination? Is E1 elimination favored by a strong base? What is? E2. And do I have a strong base here? Yeah. So I know this is going to be an E2 elimination, right? So it's an E2 elimination, and I get a minor and a major product. And Sam just said that the major product is due to Zaitsev's rule. But where does Zaitsev's rule come from? What fundamental concept?
If it can't be stable, it's going to be stable.
And what is it that you're referring to? Well, but we're not going through a carbocation.
The transition state.
The alkene. Well, it does have to do with the transition state, that's right. But it's all about the stability of the product here, right? The tertiary alkene is more stable than what kind of alkene do we have here? Yeah. Disubstituted, right? So here we have a trisubstituted, and here we have a disubstituted. So I may have said tertiary here, but it's trisubstituted, right? And Allison mentioned the transition state. So why is the transition state for this more stable than the transition state for that? Because in the transition state of an E2 elimination, what's being formed in the transition state? The carbon-carbon double bond is starting to form, right? And so the more substituted that carbon-carbon double bond is going to be, the more stable it's going to be, the lower the energy of activation, right? Exactly. So we have the trisubstituted alkene as the major product versus the disubstituted, okay? And we've also talked about being able to eliminate water from an alcohol. And this simple little alcohol, which is 2-butanol, okay, mix it with some sulfuric acid, you get 3 products. Why is the one that's listed there as the major product the major product? There's 2 reasons. Why is it? It's trans and it's also disubstituted, right? So these are going to be the biggest chunk of the mix because they're both disubstituted, right? This is going to be just a minor product. But of these, this is going to be a vast major product. This is going to be something like 95%, 4%, and let's say 1%. It's going to be approximately where these things come in, okay? So here we're eliminating HBr, here we're eliminating H2O. So we know how to make alkenes. Would this be an E1 or an E2 elimination? This one on the bottom. And it'd be E1 because we got a strong acid, and what else? It's dehydration, yeah, and what else? Well, it's not going to shift here. It's going to go through, secondary carbocation is the most stable that you can get out of this molecule. Nothing can shift. But how do you know it's going to go through a carbocation? What kind of alcohol is it? It's secondary. And is secondary carbocation okay? Yes. So it's going to protonate the alcohol, the water's going to leave, you're going to end up with a secondary carbocation, which cannot rearrange to a more stable one, okay? That's as stable as you can get here, and then you end up with the elimination. All right, so we can do exactly the opposite. We can take a carbon-carbon double bond, and we can add things across that carbon-carbon double bond. And right now, we're just using something general, like X and Y, and we're going to learn a lot of different X's and Y's, okay? But we can add things to the pi bond. We say that this reaction is ideal or atom economical. Why is this an ideal reaction? I get it all back, that's right. So everything that I put into the reaction mix, I get back out in my product. Your boss, when you go get a job, loves these kind of reactions. I buy a train load of alkene, I buy a train load of XY, I mix it together and I get 2 train cars full of product. I don't have anything going down the drain, I don't have anything that I have to dispose of, in theory, right? Perfect reaction in a lot of senses. Why is this reaction not drawn as an equilibrium reaction? Why is it drawn as if this goes to completion as drawn? It does go to completion. Now tell me why. Why do all reactions that go to completion go to completion?
Because it goes back, they would have to put in more energy.
Okay, I think I know where you're going with this. A little more though. Okay, a little more simply.
All single bonds are more favorable than just a double bond.
Why?
Because there's free rotation.
That's true, there is free rotation. This is lower in energy than the starting material, right? It is more substituted. But why is this more stable than this? So here's my alkene and here's my products. And that energy difference is pretty large, and so it goes to completion, right? There's not really much of a reverse reaction that occurs. Why is it that this product is more stable than the starting material?
Because you have less electrons shoved into a similar space.
Okay, what else? We're breaking a pi bond and we're gaining 2 sigma bonds. What do you know about pi and sigma bonds? Which ones are stronger?
Pi bond.
A pi bond is stronger? Pi bonds are pretty weak. Why are pi bonds weak? Huh? They are inflexible, but that doesn't tell me why the pi bond itself is weak. Why is the pi bond weak? The carbon-carbon double bond is actually shorter. But we're not talking about both bonds. Remember, a carbon-carbon double bond has a sigma bond and a pi bond, right? We're just talking about the pi part. That's pretty darn close. So if I look at a sigma bond, right? Those have head-on overlap of the two orbitals, right? A lot of overlap. But if I look at a pi bond, just the pi component, how much overlap do those two p orbitals have? Not a lot. Just a little bit on the edges, right? The more orbital overlap you have, the stronger the bond. The less orbital overlap you have, the weaker the bond. So what are we doing? We are sacrificing a weak pi bond, and we're gaining two strong what? Sigma bonds. And strong bonds are higher in energy or lower in energy? Lower in energy. That's exactly right. So this reaction, we say, lies to the right almost completely. 99.99999. Can you detect some reverse reaction? Sure, all reactions are reversible, okay? But the equilibrium lies so far to the right that we say it goes to completion, okay? Does that make sense? We're sacrificing a weak pi bond, but we're gaining strong sigma bonds, so the equilibrium should lie to the right, okay? The equilibrium should lie to the right, and it does, okay? Now, there's a couple of ways in which we can imagine adding our imaginary reagent XY across a carbon-carbon double bond. We can imagine adding X and Y to the same face of the alkene to where X and Y are kind of cis to one another, if you will. We call this syn addition. But we can also imagine adding one of the atoms on one face and the other atom on the other face in what we call anti-addition. And it turns out that certain reagents will do syn addition and certain reagents will do anti-addition. And you have to know the difference. You have to memorize some of these reagents and you have to know what their characteristics are, okay? You have to know that hydrogen, H2, adds in a syn fashion across an alkene, okay? And we'll learn more about why that is later, okay? But as you're studying this, you need to commit to memory how the reagents behave with an alkene, okay? And again, you can make a roadmap, works really well for this, okay? So this is by no means exhaustive. We will learn some others as well. In fact, we'll put another one up here in just a second. But in all cases, I'm taking this weak pi bond and I'm going to add something across it. I can add HX across a carbon-carbon double bond and I get an alkyl halide through a process known as hydrohalogenation. That is exactly the opposite of dehydrohalogenation, right? So we can add HCl, HBr, and HI across a carbon-carbon double bond. What's absent there? Fluorine is absent, that's right. We cannot add HF across a carbon-carbon double bond with this method anyway, okay? So we can add HCl across a carbon-carbon double bond. We can add HBr across a carbon-carbon double bond. We can add HI. If I add HI across a carbon-carbon double bond, what do I get? What is it? It's an alkyl iodide. If I add HBr, I get bromide. If I add HCl, I get a chloride. That's right. So I can make alkyl chlorides, alkyl bromides, and alkyl iodides by the addition of HX across a carbon-carbon double bond. I can hydrate a carbon-carbon double bond by adding water across the double bond, okay? Notice something here, though. If I take an alkene and I place it in water, nothing happens. I can go into my lab right now and get an alkene, put it in a glass of water, set it on this bench. We can come back in 100 years and it'll still just be an alkene and, floating on water. Okay? It does not spontaneously hydrate. But if we add a little battery acid from our car, a little sulfuric acid, it goes really well. What's the role of the sulfuric acid? It's a catalyst. That's exactly right. It lowers the energy of activation for this reaction. Okay? So we need a little bit of sulfuric acid. This is exactly the opposite of what you used before. How did we dehydrate an alcohol? What did we use? We use sulfuric acid, right? And we use it concentrated. You add it to concentrated sulfuric acid and it removes the water. Here, are we using concentrated sulfuric acid? We're using dilute, just a little bit, okay? And so we can drive the reaction in the direction that we're looking at. We can actually add halogen across the carbon-carbon double bond where we have either two chlorines or two bromines on adjacent carbons. This is called halogenation. You can add X2 across the double bond. What is absent there? Iodine and fluorine. Iodine will add to a carbon-carbon double bond, but it reverses quickly because the carbon-iodine bonds are actually pretty weak. Okay? So it's only practical for chlorine and bromine. If you take this alkene and you put it in the presence of F2, does anybody know what happens? Kaboom. It explodes. This is not a very friendly reaction. Okay? So for all practical purposes, you can add chlorine across a carbon-carbon double bond, or you can add bromine. We can also add an OH and an X. This is known as a halohydrin. Okay? Where does the OH come from? Pardon? It comes from the water. And where does the X come from? It comes from the halogen, right? Notice there's no stereochemistry shown here. We're going to learn that as we go on. Right now, you need to know what you can add across a carbon-carbon double bond. And we can also do this method right here, which is known as hydroboration oxidation. It's a sequence. What is it similar to? What have we added across a carbon-carbon double bond here? We have formally added water across the carbon-carbon double bond. But I did this through a two-step sequence known as hydroboration oxidation. Why do you suppose we need to have a second tool to do the same thing that water and sulfuric acid can do?
Sometimes you won't have sulfuric acid.
I can pretty much still get sulfuric acid anytime I want. It's a huge industrial commodity. Maybe that's something about how the hydrogen and the OH are added in the chemistry. Here you can't tell the difference. But we're going to see some examples where we want the OH to go onto a particular carbon. We may have to use water and sulfuric acid, or we may have to use hydroboration oxidation. Okay? And then there's another reaction that should be on this list, and that is the addition of hydrogen across a carbon-carbon double bond. So hydrogen gas can go to the alkane, so I can take alkenes to alkanes very, very easily through what's known as hydrogenation. Okay? However, if Nathan comes into my lab and takes an alkene and puts it into a flask and adds hydrogen gas to it, and he bottles it up so the hydrogen gas doesn't escape, and he comes back 10 years from now, nothing will happen. It'll still just be a flask full of hydrogen gas and the alkene. What do we need? We need a catalyst. What are the catalysts for this type of a reaction? Anybody remember from your reading? Pardon? Platinum is one. So in the presence of platinum, this reaction will occur quite well. Anybody know what another one was? Platinum or what? What other metal might work? Everybody's looking at the periodic table. Where's platinum at? So what else might work? There's platinum. Well, typically, do we expect the same type of chemistry as we move left to right? We expect families to have similar chemistry, right? So what might work? Palladium or nickel. There are others, but these are the ones that I'm holding you responsible for. Okay? Sometimes you will see palladium written as palladium/C. It just means palladium finally divided on carbon. Okay? What can you tell me about these metals?
They're expensive.
All but which one? Nickel. How do you know that? You got nickels in your pocket, right? You're not going to have a nickel that's worth 20 bucks, right? But platinum and palladium are very, very expensive. A lot more expensive than gold, actually. Okay? Gold's cheap on a chemical level. Okay? But platinum, palladium, or nickel can actually do this reaction very, very well. Okay? And we call that hydrogenation. Where have you heard about hydrogenation before in like your nutrition stuff? Pardon? Vegetable oils. What do they say? Partially hydrogenated vegetable oil. What do vegetable oils have a lot of? A lot of double bonds, right? And so I'm not going to draw an accurate representation, but you'll have lots of double bonds in vegetable oil. That's what keeps it liquid. That's the difference between vegetable oil and lard, is the double bonds. Right? The physical state of the two, right, is what? Liquid versus solid, right? Crisco is a solid mass, unless you're buying the liquid stuff, right? And then your virgin olive oil, right, is a nice liquid. What do they do with partially hydrogenated vegetable oil? Why do they partially hydrogenate it? To make it more solid. That's exactly right. So you want to take the vegetable oil, which isn't derived from an animal source, but you want a solid substance from it. So you partially hydrogenate the double bonds until it becomes solid. Do you know what they use to partially hydrogenate it? That reaction right there. They use an active metal catalyst, they use hydrogen gas, and they pump through whatever vegetable oil that they're talking about. And they will reduce by adding hydrogen to some of these double bonds and affect the chemistry. We can go from a solid to a liquid, or excuse me, a liquid to a solid. Okay? So you've heard a lot of these terms before. If you read on some of the it's usually not printed on a bottle, but if you look it up like on a website, you can find what's known as the bromine number for vegetable oils. Anybody know what that means? The bromine number. Well, we can add bromine across the carbon-carbon double bond, right? And what they're doing is they're measuring how much bromine the vegetable oil on a per gram basis will absorb and become an alkyl bromide. That gives them a sense of how pure the vegetable oil is. Let's say Jamie Lou is selling me vegetable oil and she claims that it's extra virgin. What does that mean? Yeah, really good stuff, right? I know that olive oil, for example, should have so much unsaturation, that is double bonds, per gram. I can test that by titrating it with bromine. I know about how much bromine that should take up if she's telling me the truth, right? And I can do a titration, just like you did in general chemistry. They sit there and do a titration with bromine, and that gives them a bromine number. If it falls outside of a certain range in that bromine number, you're selling me bad stuff, okay? And that's how they test it, okay? So it's just nothing more than simple addition chemistry across carbon-carbon double bonds, chemistry that you all are learning, okay? So we can add HX across that carbon-carbon double bond. In this particular case, since both carbons are identical, does it matter which one gets the hydrogen and which one gets the halogen? No, doesn't matter at all. And so one of the carbons is going to get the hydrogen, the other carbon is going to get the halogen. What do you suppose the intermediate is? Do I add hydrogen and halogen at the same time, or do you think it happens stepwise?
Probably stepwise, because hydrogen reacts a lot differently than halogen.
Okay, we're probably going to be dealing with a stepwise process, right? We have a polarized bond. Will everybody agree with that? So we've got a partial positive side, we've got a partial negative side, we've got a carbon-carbon double bond with the pi electrons. What do you think that first step is going to be in that reaction? How? How would you push arrows? Okay, we're going to go from the double bond to break it, and we're going to push what kind of arrow? A single barbed arrow or a double barbed arrow? It's a double barbed arrow. And why is it a double barbed arrow? That's right, there's a pair of electrons in that pi bond, right? And I'm going to move those to what? The hydrogen or the halogen? The hydrogen, that's right. And so we're going to put the hydrogen on the alkene first. And in doing that, I'm going to be left with what?
Carbon with a partial positive.
Partial? or full? A full carbocation. That's right. We're going to get a full carbocation in this reaction plus X minus. Right? And then the X minus just attacks the carbocation, and that's how we end up with the alkyl halide. The mechanism is really simple. But what about that mechanism is going to cause you to pause?
What if it's a bigger one and the carbocation rearranges?
Okay, that's right. So what if we form, we are going to form a carbocation, but once we form it, we have to ask ourselves, can it form a more stable carbocation, right? And the cardinal rule of carbocations that I gave you was what? Yeah, that's a one-word definition, okay. But how did I define it? If it can rearrange to what? There's a little more, to a more stable carbocation, it will. That's right. So that's the cardinal rule. Whereas Gabby says, yes. Okay. So in these cases, right, it doesn't matter which carbon gets the hydrogen because both carbons are identical, right? So one carbon gets the hydrogen, one carbon gets the halogen, and we've just added HX across the carbon-carbon double bond. How would you name this alkene? Give me the name for that. No. There is no center anti here. What's the IUPAC name? Ethene. That's right. The common name is what? Ethylene. And we're adding HBr across it, and so we're going from ethene to, how would you name this? There's two ways to name it. What's the, pardon? Ethyl bromide is one way to name it, and bromoethane, right? Why don't I have to say one bromoethane?
You flip it around and it becomes.
Still the same, right? That's right. So there's no difference. Here we're taking, what's the name of this alkene? Cyclohexene. We're adding HCl to it. We're getting chlorocyclohexane, right? Or cyclohexyl chloride. But chlorocyclohexane works well enough for me, okay? The mechanism is exactly as we've discussed, okay? So here we've got cis-2-butene as our reactant. We're going to break the weak pi bond, and we're going to push those electrons to the hydrogen. Hydrogen can only have how many bonds? One. So as the pi bond reacts with the hydrogen, the halogen has to leave, right? That kind of looks similar to what kind of reaction that we learned about. If we think of the pi bond as a nucleophile, this is kind of like an SN2 reaction, right? Except it's on hydrogen, right? So we've got the pi bond reacting, the halogen leaving. We end up with a carbocation. We pause. We ask ourselves, can that carbocation rearrange to a more stable one? And the answer here is no, it cannot. And now the bromide attacks the carbocation and forms a new carbon-bromine bond, and we're done. It's just a two-step process.
So the pi bond breaks before the hydrogen bond.
This is kind of happening at the same time. Yeah, so as these electrons are reacting with the hydrogen, the bromine is leaving. That's why I said it's kind of like an SN2 reaction, okay? It's not an SN2 reaction, but it's kind of like an SN2 reaction. We end up with a carbocation. It's secondary. It can't rearrange to a more stable one, and now the bromide simply attacks, and we end up getting a new alkyl halide. This is nothing more than a series of acid-base reactions. It's just that simple. What's the acid and what's the base in the first step? The acid is the H of HBr. That's right. What's the base? The pi bond. That's exactly right. It's a Lewis base. It's donating a pair of electrons. Lewis acid, Lewis base. So a Lewis acid, Lewis base is going to give me a conjugate acid, conjugate base. What's my conjugate acid? What's the conjugate acid, Sam? That's right, because that's the electron pair acceptor. And what's the conjugate base? The bromide. So I have Lewis acid, Lewis base, conjugate acid, conjugate base. And so now my Lewis acid on this side reacts with the Lewis base, and I end up with my product. It's nothing more than Lewis acid, Lewis base chemistry. It's just 2 steps of it. Okay? Any questions about that? Okay. Life isn't always that simple. Actually, the mechanism's always that simple. Okay? But in this case, what's not so simple? The 2 carbons of the alkene are what? Identical or non-identical? Non-identical. And so if the hydrogen goes on, let's say, carbon 2, and the chlorine goes on carbon 1, we would end up with 1 chloropropane. But I can also push arrows on a piece of paper where the hydrogen goes to carbon 1 and the chlorine goes to carbon 2, and I would end up with 2 chloropropane. Are those the same or different products? They are different. One is a primary alkyl halide, the other one is a? This is a primary alkyl halide, this is a what? Secondary. This is the only product we get. We only get 2 chloropropane out of this reaction. It is. That's true. Well, what is, though? The product or the intermediate? The intermediate, that's right. This comes to another rule. And early on in chemistry, it was all a bunch of Russian rules. We've heard about Zaitsev. And now, in addition chemistry, we have what's known as Markovnikov's rule. Okay? Markovnikov's rule simply states that the addition of HX to an unsymmetrical alkene, the hydrogen atom bonds to the less substituted carbon atom. Or as a lot of students like to remember it, the carbon atom with the most hydrogens gets the hydrogen. Okay? Huh? You can think of it that way. That's an oversimplified statement. What really is governing that rule? Danielle was hinting at it here just a second ago. Why is it that that hydrogen goes to the carbon with the most hydrogens? Okay, but what about that? Okay. So we have to draw both of them out. Let's suppose the hydrogen goes here, right? And I'm just showing the one hydrogen. Of course, there's 2 others there. What kind of carbocation is that? Secondary. But now, what if we put the hydrogen here? What kind of carbocation do I get? Primary. What's more stable? Secondary. Markovnikov's rule is really all about carbocation stability. Very important, okay? So the hydrogen is going to go to the carbon atom with the most hydrogens, because in doing so, you'll end up with the most substituted carbocation, okay? So let's look at another quick example here. What's my product going to be? So let me number where's the hydrogen going to go and where's the bromine going to go? Because of what rule? Markovnikov's rule. That's right. That's the product we're going to get. So if we're going to go through the mechanism, right, we're going to have the electrons from the pi bond react with the hydrogen. The hydrogen's going to go to carbon number 1. Giving me what kind of carbocation? Tertiary. Can it rearrange to a more stable one? Nope, so it stays there. And now what happens? That's right. These mechanisms are not difficult, but you have to take them step by step. You have to pause and ask yourself, can the carbocations rearrange? Okay? So we've just talked about that, so we'll skip. We just did that on the board, right? Now let's look at an example here. Here we have 2-ethyl-1-pentene. Notice the carbons of the alkene. One of them has 2 hydrogens attached to it. The other one has 2 alkyl groups. And Brienne wants to add HCl across it. Where's the hydrogen going to go? Carbon number 1 or carbon number 2? The hydrogen goes to carbon number 1 because Markovnikov's rule. That's right. The chlorine's going to go where? Carbon number 2. Notice in adding that chlorine to carbon number 2, what did we just generate? A chiral center. So we should be able to have both R and S enantiomers, right? And so Jamie Lou runs this reaction. She gets her product. She goes to the polarimeter, and what does she notice? It's racemic. It does not rotate plane polarized light. Okay? Your homework to think about for Wednesday, when we start Wednesday, okay, is to tell me why we get a racemic mixture out of that reaction. Okay? So that's it for today. I will have your regrades on exam 2 back to you Wednesday. When did we set the deadline for the